Okay, greetings detectives. Here's part 2. Now, you should have your assignment text, student assignments text from the skinny book, page 57, and the top of it says, "Thank goodness Descartes didn't drink some warm milk, graphs of sequences." Triplets, question number 1 says, seem to run in the Tribbiani family. Great-grandma Tribbiani is one of a set of triplets. She had triplets, and each of them had triplets. The sequence shows the number of descendants in the Tribbiani family over several generations if this trend continues. So we can see it goes 1, 3, 9, 27. So how would you describe this sequence? Well, I would describe this sequence as geometric. And I would say that the common ratio, because it's being multiplied, each term is being multiplied by something, and it's being multiplied by 3. Okay, so the common ratio is 3. So if we wanted to write an explicit formula to represent this sequence, we could go back to our original notes, and we could look up here and see that an explicit geometric formula is G sub n equals G sub 1 times the common ratio to n minus 1. So let's go back and let's see if we can write that. So I'll just write it here. G of n equals G sub 1 times the common ratio to the n minus 1 power. All right, so let's go ahead and do this. So G sub n equals my first term, which is 1, times my common ratio, which is 3, to the n minus 1 power. All right? Let's see if that works. If we put our first term in, term 1, we would say, if we were trying to find G sub n, we would do 1 times 3 times 1 minus 1, 3 to the 1 minus 1 power. Well, this is something you may not know, but any number to the 0 power, that's a 0, equals 1. Okay? Doesn't matter what we have, if it goes to the 0 power, it's equal to 1. All right? So that's an important thing to know. So 3 to the 0 power is 1. 1 times 1 is 1. Let's try, so let's actually start creating this table. Term 1, the value is 1. Term 2, the value is 3. Term 3, the value is 9. Term 4, the value is 27. Well, let's see if we put term 4 in our little explicit formula, if it would work. G sub 4 is equal to G sub 1, which is 1, times R to the 4 minus 1 power, so that would be 3 power, and R is 3. So 3 to the 3rd power would be 3 times 3 times 3. So 3 times 3 is 9, and 9 times 3 is 27. 1 times 27, G sub 4 is 27. So now what I'd like you to do, using whatever method you'd like, if you want to use the just knowing that you're going to multiply this, the recursive, you multiply times 3, right, to get to the next one, you can do that. But I'd like you to find terms 5, 6, 7, 8, 9, and 10. If you want to use a recursive, you can. If you want to use the explicit, you can. But either way, I'd like you to fill this in. And please, please use a calculator. So I'm going to pause while I fill this in. You pause as well, and you fill your table in, and then we'll compare. Okay, I filled in my table, and you can compare yours to mine, and I'm just going to pick the 10th term, and because what I did was I used the recursive formula. I just kept multiplying the previous term by 3 to get the next one, because to me that was easier than plugging everything in. But just to make sure that I did it right, I'm going to pick the 10th term, and I'm going to use my explicit formula. So I'm going to say G sub 10 is equal to 1 times 3 to the 9th power, right? Because 10 minus 1 is 9. So I'm going to go into my calculator here and I'm going to say 1 times 3. Well, if it's going to be multiplied by 1, I don't really need that 1 at all. So I'm going to say 3 to the 9th power equals 19,683, and that's what I have written there. So I did my math correctly. Hooray. All right, so now that I have my table filled in, I can go to the next page. And for you, I think it's just turning it over. So now I'm going to use each pair of numbers from the table as an ordered pair and graph the ordered pairs on the grid shown. So let's see. I need to look at my numbers. So I got 1, 1, 2, 3, 3, 9, 4, 27, 5, 81. I think I'm going to start with my 10, because that I think is going to be easier to do than my 1. 10, 19,683. So I'm going to go to here. And let's see. At 10, I'm at 19,683. So it looks like it's 1,000, 2,000, 3,000, 4,000. So every mark, every hash on that grid is 1,000. So this would be 19,683 is going to be somewhere. The very top is going to be 20,000. So at 10, I'm just going to say it's right about. Ooh. See if I can do this without marking up my page here. 10, be right there. Okay, so there's my 19,683. Now, the 9th one, I'm just going to go backwards, is 6,591. 6,591. So that's going to be between 6 and 7. So if here's 9, I'm going to put it right about there. Okay. And then my 8, whoops. My 8th is 2,087. 2,087, so there's 2,000. 87 is still very close. Was it 87 or 800? Let's see. 2,187, so it's still very close. Still very close to 2,000. It's not as close to, it's closer to 2,000 than it is to 3,000, so I'm going to put it right about there. And then my 7 is 729, so 7 is going to be close to 100, sorry, to 1,000, so I'll say it's right about there. And now I'm starting to get very, very, very close to my x-axis, aren't I? Especially the way it's written here. So then I have, oops, wrong one. 5 is 81. 5 is 81, so now we're just looking like it's just really, really, really close. I'm not even going to try. It's so close. It looks like it's on the axis, but it's not, okay? And it looks like it's going up, but it shouldn't be. So we're getting very close to 0. So you can see what's happening. You can look at my graph. So describe the shape of this graph. What would you say this graph looks like? Well, I would say that it is a curve, that it's discrete, and it increases. Yes? And actually, it asks us a question down here, is the graph discrete or continuous? And explain your reasoning. We'd say discrete. And why? Why don't you explain your reasoning? We're going to say that it's discrete because terms are integers, not fractions. Remember, our term numbers, we don't say there's a 1.5 term, right? If we look here, our terms were integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There weren't any negatives, but there could have been, all right? But at this point, we're saying that they're just, actually, it'd be unusual to see a negative term, wouldn't it? So we can actually go back to our question and say that they're not even integers, they're whole numbers, right? Okay. So now we have to use that explicit formula to predict the number of descendants in the Tribbiani family in 20 generations. And we could do that, couldn't we? We would say G sub 20 is equal to 1 times 3 to the 19th power, and we would just simply clear this. 3xy to the 19th power equals, whoa, let's see, we're looking at 1,162,261,467 descendants. So that's a lot, right? And I don't even want to write all that down. So you write that down on your paper. I'll leave it up for you to copy, or you can pause it. Okay. Okay. So now it was 1 billion plus. You write the actual number, okay? The last thing I want us to notice, though, is I want you to see if you can look at that graph and if you can see that it's a curve that's going straight up. It's going straight up. And what kind of graph, do you remember what kind of function that was? It wasn't linear, it was exponential. So that's the other thing that we want to recognize about geometric sequences, is that they are exponential graphs. Now, if we wanted to write this equation, this formula, we could write it as an exponential function, but it's going to take a little bit of work. So I'm going to just quickly go through it, and I want you to just watch it, and I'm not asking you to memorize this, all right? I'm not asking you to memorize it. I just want you to kind of get used to this. So G sub n, if we change G sub n to f of n, because we're going to turn it into an exponential function, we're going to say it's the same as 1 times 3 to the n minus 1 power. Well, how do I take 3 to the n minus 1 power and actually move it around so I don't have that n minus 1 thing? Well, let me show you what I mean. I don't need to worry about the 1, so I'm going to say that it's 3 to the n times 3 to the negative 1 power. So basically what I did was I broke up my n minus 1, and I created two separate numbers, 3 to the n and 3 to the n minus 1. Now what I need to do is I need to get rid of my negative exponent, and you may or may not have learned this, so I want to make sure that you just kind of are exposed to it. And I'm going to say that, I'm going to write it up here, 3 to the n times 3 to the negative 1 power is really the same as 1 over 3 to the first power. So when we have negative exponents, they really turn into fractions, okay? And this becomes, so that's just really 1/3. And then we have 3 to the n times 1/3, all right? Well, 3 to the n times 1/3 would just be 1/3 times 3 to the n power, which is equal to f of n. So there is my explicit equation turned into a function. And if you kind of think back, you'll remember that an exponential function always had your x value or your independent value in the exponent. And so now it's up there. And just to remind you, the equation of an exponential function is f of x equals a times b to the x power. So what's our a? 1/3. What's our b?